Our first speaker is Mr. Anderson, I believe. And so, let's start. Thank you.
What I wanted to share with you is a work in progress. And we are about halfway through this project. I kind of wanted to show you where we are, and the analysis is still ongoing, but it is an interesting project nonetheless, and one that I'm hoping that the DMT comes out to be the winner in. It's more or less testing for the estimation of lateral earth pressure in Piedmont soils. So what we're going to talk about just briefly is what are the potential for earth pressure in Piedmont soils, and then why we're doing this research task. Kind of give you an outline of the things that we're doing. Go through the in-situ testing we've done for this portion of the study. Show you how we did some field instrumentation and construction to tackle this problem. Show you the steps of how things worked out in the excavation, and then kind of show you where we are with our analysis and what we're planning to do in the future. So with the earth pressure in Piedmont soils are residual in nature, and this area is probably part of the Piedmont, and it stretches all the way down to the Atlanta area. And residual in nature means it was not transported. That means it weathered in place, and there are inherent properties of that soil that have to do with the fact it was weathered in place and it was not transported. North Carolina, the parent formations, there's some igneous metamorphosed and some originally sedimentary materials that have become decomposed in place. And they're often classified. If you were to just to sample these materials and do a grain size distribution, you basically get something that was either probably right on the verge of silt and clay. Even from our site, some of the samples have come back silt, some come back clay, but relatively even fractions. And you can see the swath that represents the Piedmont. It starts, it really takes in D.C., a good portion of Virginia, central North Carolina, South Carolina, down into Georgia and Alabama. So tackling this project in North Carolina was pretty big because we really have a lot of this stuff to deal with. And you can see in North Carolina the primary zones. You can see that the far east is the coastal plain. It's kind of the sandier areas, and the far west, of course, are the mountains and the rockier soils. With that swath that runs up the middle, the brown, the red, and the gray are three predominant residual soil zones. And the areas that we've worked in, we're looking at the Charlotte Belt, which has to do primarily with the parent rock materials, and then the Carolina Slate Belt. And the thing about Piedmont soils that become a challenge for us as geotechnical engineers is they don't fit into those nice original bins that we created called sand and clay. They don't behave like sand and clay. And they may exhibit a mixture of both behaviors depending on the relative fraction of the particle sizes, but they also have some evidence of what we would originally call a cohesion, or some kind of an intrinsic shear strength and it's whether it's due to particle interlocking, which is probably more than likely with the original fabric that's there, or maybe even some suction or negative pore pressure within these materials. And here's a sample of when we excavated. This is the kind of stuff that we found pretty much everywhere. Still retains a lot of the original rock formation, but it crumbles. It's soil. It's all decomposed. So where we came in with this project is NCDOT came to us and said they want to measure the earth pressure in Piedmont soils, and because they do quite a few retaining structures in this area. They do pile panel walls, MSE walls, and some shoring walls. And there's visual evidence, and you'll see a little bit later in some of the photos I've got. There's visual evidence. The engineers came back to the office and said, "Hey, wait a minute. There are plenty of near vertical cuts in this zone that have been standing for 30, 40 years with a structure on top of the cut." And we're going back and we're designing these walls. We're designing these cuts to have walls. So there's got to be some rationale for getting these, coming up with a whole new idea on how to do the design. And what DOT does currently is when they're in the residual in the Piedmont zone, in order to design a retaining structure, they go back to just a sand earth pressure diagram. So that they ignore any cohesive effects, any interlocking effects, and they estimate the friction angle based on an SPT blow count. They develop an earth pressure diagram, and that's what they use to design these retaining structures. But if you think about these Piedmont soils, they've got something intrinsic. They've got some intrinsic interlocking. And again, it could be due to suction. It could be due to soil fabric that is holding these soils together, and we don't get anywhere near the earth pressure distribution that we have with the sand. It probably looks more like what you would expect from a ranking clay distribution, where we have a zone of no pressure, maybe, or a negative when we have some tension cracks, and then a positive pressure as we get down deeper. And we'll see if we can get some evidence of that. So the research concept, again, DOT came to us. They said they wanted to develop an earth pressure model for designing retaining structures in Piedmont soils. And they came to us with the original thought that they want to instrument some MSE walls and use earth pressure cells. And we talked to them and said, look, instrumenting an MSE wall is not going to get them where they want to go, because that's going to be a wall that's built and then backfilled with some select material, and you're not going to find out how those residual soils behave. The only way that we're going to figure that out is if we do some kind of a top-down construction. If we insert a wall directly into the Piedmont soil and try to do some measurements. So they wanted to measure the earth pressure. Earth pressure is a very difficult thing to measure, especially in the Piedmont. They wanted an in-situ measurement, so we had to do top-down construction. So the only thing that we could really get our teeth into was we proposed to build 3 instrumented sheet pile walls in the 3 Piedmont soil provinces. The 3 instrumented sheet pile walls that are meant to have a factor of safety of near 1, so they would move and we would get some kind of a, if the earth pressures, if the soil behaved in the way that they traditionally designed for, we would get enough deformation that we'd be able to measure the bending in the sheet pile walls and back figure what the earth pressure was. And the goal was to develop some simple model for earth pressure in Piedmont soils based on the results of these full-scale wall tests and some in-situ soil tests, possibly a dilatometer, CPT, borehole shear, or even a step blade. And I want to make a comment here, is that when we originally approached, when DOT and I were discussing this project, they were not very interested in doing a lot of in-situ tests. Their opinion was, we're going to do SPTs, we want to come up with something that's going to be related to the SPT and maybe some other qualitative measure. And then after this project got underway, we took it upon ourselves to do dilatometer tests. They actually had a borehole shear tester that we used, and then Roger loaned us his K-Knot step blade. And after seeing that they could get a lot more information, they've actually opened their eyes and are very positive about using the dilatometer. So that's where we're hoping the link will be made. So what we've done in the project is we've kind of piggybacked on other construction that's going on in the state. And the first selection of a wall was near Statesville, North Carolina. And Statesville is, this is Charlotte, this is Mecklenburg County right here. So Iredell County is just north. And it just so happens that the site that we had in Statesville was right on the boundary between 2 belts, between the Charlotte Belt and the Inner Piedmont. And I think that even we had a geologist from DOT working with us to map the soils, and he said it was just basically the transition of those 2 zones is where we were. So let's look at some of the tests that we did, and just kind of the DOT provided a standard penetration test. We performed dilatometer test. SNME donated some CPT work. We did borehole shear tests and attempted to do a step blade test. There's DOT. Really good job doing the drilling. And this was our geologist. His name's Clint Little. They say he's the kind of guy that can just walk out to the site around there and look at the ground and tell you how far rock is. He's a real talented geologist. So, here's doing the dilatometer test. The first time the drill crew had ever seen a dilatometer before. I know a lot of you have been in that boat before. And a lot of the challenges that you find with the drillers these days is these guys wanted to use 10-foot rods. And actually one drill crew showed up with nothing but 10-foot rods. So trying to push a dilatometer with 10-foot rods was quite a challenge, just getting enough slack in the cable and being able to get a load cell up on top of 10 feet before you push. But hey, we made it work. So SNME brought their new truck out and did some CPT soundings for us. And here's the results. Sorry, this is kind of small, but I just wanted to give you some comparison. The dilatometer thrust, the P0, P1 values, the KD. You can definitely see the crust there, the desiccated crust and the KD values. Material index you see between 1 and 2, probably a little bit less than 1 consistently. ED, very constant with depth. And then the CPT, again, this was a very uniform site. For a Piedmont site, which those of you who work in the Piedmont know that this can be a very undulating, unforgiving type of material. This was an excellent research site we kind of stumbled upon by accident. Even the blow counts here were all fairly consistent, even for an SPT. And if you look down to about 4, I think I have meters here, about 3 meters depth, it was kind of a browner, desiccated crust material, and then we got into kind of a redder looking residual clay or material with depth. And this is just a second side showing you we had 2 clusters, and I'll show you the 2 clusters in a minute. This was the second clustered set of tests, and we actually did 2 dilatometers and 2 CPTs in that area, and then they were 20 30 feet apart, and we still had fairly consistent readings. And also even with the SPTs were fairly consistent, so it was much better repeatability even with the SPT than I would have expected. Borehole shear test, we actually only were able to successfully do 1 borehole shear test because of some confusion with the drillers as to how long their augers were. We kind of argued about how long the augers were, and I think that the borehole shear test, some of the ladder tests ended up on the bottom of the hole, so we were actually testing the bottom of the hole and not the whole wall. And then the machine ended up getting, I think, heat damaged, so they're having it repaired for the use on our next test. So, but the results of the borehole shear test, the good hole were promising. These were the 5, 10, and 20 foot depth borehole shear test, 41 degrees friction, and this was in the shallower, the browner, siltier material, 31.9 PSF, 129 PSF, and 226 PSF cohesion from the borehole shear test. So we think this is a promising finding from the borehole shear tester. And then we attempted to do the K-knot step blade. I thought that this was going to be the thing that would tell us the most. But I think what we found out was that there were so many, the fabric and the particles that were remaining in the fabric there were probably too large for the discs on the K-knot step blade, and we got some very bizarre numbers. We were getting K-knot values of 28 and 30. And even though I actually talked to Handy about it, and he said it's not uncommon in Piedmont in the residual materials to get fairly high K-knot values, but we really didn't get a very warm, fuzzy feeling about it. So again, difficult to run, and the results of the initial tests were inconsistent, no further K-knot testing. And just happened to be that day that the head honcho from DOT was out watching us bumble through the step blades. And what we ended up with then, when we planned to build our walls, if we go back and look at the wall plan, this is where our tests were clustered. We had a fairly tight cluster here of a borehole shear test, CPT, dilatometer, SPT. So this was a good soil comparison cluster right here. And then cluster 2 was more or less this side of the wall, with 3 dilatometers, SPT, CPT, and what have you. You'll see a little bit later. Just remember, kind of towards the center of the walls are important areas to have done testing, because those are where our instrumentation is going to go. We took the results of DMT and CPT tests because we were more confident with those, and we just went in and did some basic earth pressure calculations based on. And you can see we took just the equations, the Bilotti and Marchetti equations for K-naught, and calculated what the earth pressure would be. And then we determined what the friction angle was, and we just went back and estimated what the active earth pressure distributions would be from the dilatometer and the CPT also. And this is just to give you a point of reference. This is what we thought we were going to get just based on the in-situ test we did at the site. Well, we wanted to build these walls to to measure the earth pressure. I kind of call them moment cells because it's just like a lighter loaded pile. If anybody's ever done any strain gauge reduction with a lighter loaded pile, we're doing the same thing. We're going to measure the bending in the wall, and we're going to back figure what the earth pressure is. So we had to get out there and measure the bending of the wall. So we got to build 2 test walls. So what we're going to do is we're going to construct 2 PZ22 sheet pile walls that were a minimum of 30 feet apart. Walls are to be instrumented to measure strain using some vibrating wire strain gauges, and then we were going to have a backup just in case the strain gauges all got destroyed. We wanted to have inclinometer. We had a very low-tech way of doing inclinometer that was very cheap, but gave us a good backup of our strain gauge data. And from the measurements, we wanted to estimate the shear distribution or the earth pressure behind the wall. So here's what you would expect from a vibrating wire strain gauges. We were using the same geocon gauges. You can see they're go ahead, Roger. And what we'll get from those strain gauges is a moment distribution with depth. And then if you do 2 derivatives of that moment distribution with depth, you can back figure what the soil reaction is. And that's the approach we were going to take to determine the soil reaction. And then we were going to go back and use a slope inclinometer. Most of us are familiar with that. Again, it's just a kind of a tertiary backup just in case we lost everything. We'd at least be able to know what the deflections were, and we could go back to our models and say, well, we were conservative because we thought there were going to be this many inches of deflection, and we had this many. It would just be more of a qualitative estimate, and it also helped us do some very quick, safe measurements. We're putting people down in a hole, and we had to be safe. We had to be able to tell these guys down the hole how safe they were at any time. And the inclinometer kind of gave us that immediate feedback that we could come back and download the data real quickly and say, this is how much deflection we're getting. I think it's safe to continue. So what we had to do first is determine some preliminaries. I had a student doing a lot of finite element modeling to determine what's the optimum sheet pile section, what's the optimum pile length, penetration depth, how deep can we excavate it safely, how far the walls have to be apart. And DOT definitely made sure that we took care of safety and contingency. It was a battle to get our factor of safety as close to 1 as possible and then keep the DOT happy. So what we came up with is we're going to use PZ22 sheet piles. Most people use PZ27, and they were a little bit too stout for what we wanted. We get a lot more deflection out of a PZ22, so we went with PZ22. 35 feet long. They were driven 34 feet depth with 1 foot exposure, basically for the clamping. And the minimum separation was 30 feet that we specified. And we were going to excavate these sheets 20 feet. So there was going to be a 14-foot embedment after the excavation. And the DOT wanted to have an additional at least 20 feet of wing walls to protect the excavation, to protect a hauling road for escape purposes. The only other work we could find that people had done something of this scale was a court in the Netherlands. But he was really interested in sheet pile walls and soft soils, but he was more interested in measuring the behavior of the sheet piles and not the soil behind it. And he also used anchored sheet piles, or we're using cantilever. So what we came up with is we've got these PZ22 sheets. We have strain gauges. Each sheet has 16 gauges on it with depth, and we have 2 other sheets that have a box tube section welded onto them for our inclinometer casing. And you can see setting the gauges before we get started, welded on all the gauges, and then went back and had to pre-strain the gauges so we could get enough resolution to capture our full bending. Again, the gauges then we covered the gauges with a channel with a angle section to protect them during the driving, and it worked for the most part until actually they hit the sheet so hard that the welds popped off in one of the sections. So, what we ended up with between our preliminary model and our final design, both walls were 66 PZ22 sheets, had 132 sheet piles installed total. We had 40 test sheets. Those were the ones that were going to be driven the full length, 35 feet, and then we had 26 sheets to shore the excavation and access escape roads, and they were 20 feet long. So they made those shorter because it was going to be on an incline anyway. And we ended up with a distance between the walls of 40 feet. And this was purely by accident because we were on a very fast track. I had to go out late one night and lay out the excavation for the contractor who was coming to drive piles. And you'll see that my accident of 40 feet actually really paid off. So So after the contractor was finished, this is what we ended up with, and this was one of the unfortunate parts of the project. The way the contract had been written is there was no language in the contract about how deep the sheets actually had to go and what kind of hammer they needed to use to drive the sheets. So when they brought an extremely small vibratory hammer for this material, but the blow counts were 10 or less in most places, so we thought they were going to be able to penetrate. There were some seams of some decomposed quartz and things that were these sheet piles were taking up in a little bit too early, and in addition to having their small vibro, they had a fairly small diesel hammer, and when they put the diesel hammer on, they could drive it a little bit further, but they ended up overstressing several of the sheet piles in the top because the hammer was very small. And it was stroking about 9 feet at least, so the impact stresses of that 9-foot stroke were outrageous. So I think the next round we're going to have to put some language in the contract about getting the sheet piles safely driven down to the depth. So the bad news is, if you remember, the test sections were in the middle, and you can notice there's a ladder there. That's the ladder I had to climb to do one of the inclinometer tests. We didn't want to cut off the sheets because we intended to use them again, so we left them, for the most part, unless they were very badly damaged, we left them as is once they were driven. The good news is there's a zone right around here that were well driven, and that's where most of our measurements are going to end up being important. So just another looking the other direction. Looking back, this way is north, and then that way is west. So the northwest is the area that we measured from. So we had 64 gauges. We had data loggers recording strain every minute for about 2 weeks. Single inclinometer with a data recorder. We surveyed for an extra level of redundancy. We did a survey, and the inclinometer and surveying were done after each excavation lift. And there's the data logger student installing we had a lot of wire because we thought we were going to have to be away from the excavation, but we ended up being able to stay closer. Okay. Excavated between sheet piles 4 feet per day up to 20 feet, or when I determined there was excessive deformation. And we agreed that if there was 6 inches of deformation at the surface, then that would be too much, and we would stop the excavation. We finished construction on 9/30 of the walls. We were going to get ready to start, but Tropical Storm Ophelia came in and drenched us for about 2 weeks of rain. So that shut us down for 2 weeks, and we started on 10/17 and completed on 10/27. It took us 10 days to dig the hole out. That was the first lift. They got there the first day, got started, and the track hoe broke down. So again, the first 4 feet coming out. There's the 8-foot excavation depth. And this is what I'm saying. It was almost dumb luck that I said 40 feet. If we had been any closer than 40 feet, he couldn't have swung the boom around. So we originally said 30 feet was about the minimum for the passive wedges to develop. And I just set it out 40 feet apart, and we just really lucked out that we could get the excavator in safely. I think that's 16 feet. And that's the fully excavated pit. We had to leave a couple of berms that we hadn't intended to because these sheet piles were getting close to being exposed because they were so shortly driven. So they required us to leave some berms in there, and we also left, because this was a hauling road, this is where they brought the excavator in and out, we had to leave some berms there. We found out that may have caused us a couple of problems. One thing to notice is we started getting some separation of the sheet piles from the soil. And I actually fished this gap with the tape as far as it would go down before the tape the end of the tape was, and it would go down in some places 10 to 12 feet. So that meant there was a tension crack 10 to 12 feet deep behind the wall, at least. Go ahead. And that was I think this is the final excavation. Notice that white was one of those veins of the decomposed quartz that the SPT missed, and you can see the sheet piles. All of them took up very early because they hit that. So. Another view of the finished excavation. Another view. Again, here's another look at here's duct tape width for scale. This is another one of the gaps that developed between the wall and the soil. The reason this one's probably larger than the other is because this is on one of the very long sheet piles that was sticking up. And there's me and my research team. My guys really did a good job running back and forth to Statesville every day to do this. And it was kind of funny that in the middle of all this, this is a construction site. This is a big borrow pit from NCDOT. The contractor was doing a similar test, and he was just taking this site down about 30 feet, and he had this huge Volvo excavator on top of a vertical cut the whole time. He wasn't worried about it. So we kind of monitored that. Never saw any failures or anything, and they were surcharging that cut. So this stuff's pretty stout. All right, Roger. So we'll just kind of, way I'm going to close this up is to give you kind of what we some of the things we found out. Like I said, only the northwestmost strain gauge pile was close enough to being properly driven. A lot of the others weren't deep enough. And one of the sheet piles was actually damaged a little bit during the driving process, and we lost some gauges. Another thing is that in the contractor's zeal to get started, he went out and actually started putting on strain gauge covers before our gauges were properly set, so we lost some of the resolution on some of our gauges too. Note that the maximum deflection on the well-driven pile, the inclinometer, was actually less than 1 inch. Here's the inclinometer readings in that northwest quadrant. You can see the maximum at full 20 foot of excavation was not even quite 1 inch. So we're really not measuring much at all. And some of our predictions, and we did a lot of initial predictions, software predictions, and they range between 3 and 12 inches of deflection depending on what soil properties you were putting in there. And these undercut all of our predictions. Our bending moment profiles from the strain gauges, you can see, as we would have expected, until we get down to the last excavation step. As you excavate, we would expect that the bending moment, the maximum moment, getting forced deeper and deeper into the ground, and we're getting more of a zero stress, zero moment zone near the top. I think what happened is because of the berms we had to leave for safety, we ended up with locking that 16-foot moment into the wall, even down at 20 feet. So. And it just, after we went back and calculated the earth pressure based on those bending moments for that 20-foot excavation depth, then we went back and compared it to that plot I showed before where we estimated the earth pressure. And the active earth pressure based on the CPT and dilatometer really pretty much coincided with what the peak value was from the measured. However, it's still going to overpredict the total earth pressure because the distribution isn't quite the same. So what we ended up with was that K-Naught definitely appeared to overpredict the earth pressure in this case. The active, using the CPT and dilatometer, seemed to capture the peak value. But again, this is a work in progress. We're kind of halfway through it, and we got more analysis underway to compare some of the other raw parameters from the dilatometer to the measured distribution. I still think that's going to be our best bet in the long run, is to find a good correlation between DMT. The project does continue. We have a second site has been located in Monroe near North Carolina South Carolina border. It's in the Carolina Slate Belt, which is a little bit further east, slightly different geology, but it's still a Piedmont zone. And we're getting ready to start our second round of in-situ testing and wall construction probably beginning of the 2007 fiscal year. So. And we're hoping to build on some of the lessons we learned in this one to improve the outcomes of the second one. One is kind of the sheet pile connections. One thing I think we're going to drive the sheet piles disconnected at the escape route walls to allow more of a plane strain condition to develop on the test walls. And we're going to have to develop a better contractor hammer selection and minimum penetration depth criteria. And subject the contractor to some inspection. So, and just to show you, the Statesville was up here. The Monroe is going to be down there close to South Carolina. I think that's it. Thank you.
Thinking about it with what we learned this week with the seismic DMT and getting shear modulus degradation curves, maybe that would be a good way to predict and do your finite element analysis, be able to use them in the project. So.
The finite element program we use is Plaxis, And then we also did some predictions using Seawall SSI, which is a kind of a PY curve program for doing flexible retaining walls. So we used two. The fine element, though, was done by Plaxis. We did a lot of the upfront with Plaxis.
And I kindly ask Mr. Yang Sang Kim to present his work.
Okay, thank you, Chairman. My name is Young Sang Kim. I'm from Korea. And today I'm going to be talking about the Dilatometer dissipation analysis using an equivalential radius and optimization techniques. So Dr. Peg is my co-author of these papers. 2001, some Korean researchers started to test the application of DMT dissipation test to Korean soft soils, including me. So we found that the P2 logarithm method and DMT methods are still applicable to Korean soft soils. But we found also that some we have to modify or more improvements are needed for empirical aspect of present method. So you know that DMT methods basically developed for the Italian clays, but still applicable to Korean soft soils. But P2 logarithm method and C-square root method is semi-empirical method. It has some kind of theoretical point and empirical point. So today I'm talking about the investigation of influencing factors, for example, equivalent radius and theoretical solution, what they are used. And we would like to propose a new method of DMT dissipation analysis using an optimization techniques. By using this optimization technique, we can determine the coefficient of consolidation which reflect only dissipation trend, not the point. So actually DMT has no porosons, as you know, but many researchers has proposed some dissipation analysis procedures. So DMTA, DMTC, and A2 method. So today I'm just focusing on the DMTC method. In DMTC method, we implement the three positions and we measured A, B method, and by deflating it, we measure C pressures. Usually we do not measure C pressures, but in this patient test, we can measure the C values with respect to time. This is a calibration for the A and B, C with respect to the membrane stiffness delta A and delta B. So actually, we have two kinds of DMTC method. One is P2 logarithm method, which uses some corrected P2 values with respect to the membrane stiffness, and the C-square root method uses uncorrected C values. So this is an advantages of DMT dissipation test compared with some piezo test. Because it doesn't have any membrane filters, so it has no smearing and loss of filter saturations, and it has no cloggings. And also, you know, the piezo has measured the excess pore water pressures with 5 millimeters thickness porous tons. But DMT measures. Okay. DMT measures pore pressure or P2 values with 60 millimeters diameter membranes. So if we can determine the coefficient of consolidation with DMT, it might be representative of a large contact areas. So this is a simple interpretation of P2 logarithm method. At first, we plot the P2 versus to time log scaling, and we can normalize the P2 values with respect to the static pore water pressures. And then we can pick the T50 at the point of 50% degree of dissipation. And then we can determine the coefficient of consolidation with the simplification. Actually, this is proposed for the comes from the one-dimensional Terzaki solution, theoretical solution, but is also proposed for the piezo dissipation analysis. So you know the T50 and T50 are proposed by the many researchers, but for the cylindrical, the kind of cone penetrometers. So we have to think about the kind of which kind of theoretical time factor is appropriate for the dilatometer dissipation analysis, and we have to think about the equivalent radius of dilatometers. This is a simple interpretation of the C-squared time method proposed by Dr. Schmatman. We have to find the C0s and C100 graphically and mathematically, and then we can calculate a C50 by adding these two values and divide by 2, and we can find the square root T50. Then also we can find a coefficient of consolidation with these simplifications. I here summarize some differences between DMTC method. So actually, P2 method has some assumptions. That is, the P2 values is comparable to the penetration pore pressures around the DMT probe, and it has been proven by research DMT. So, and also they propose some use of Torstenson cylindrical solutions, and also they use the equivalent radius 20.57 millimeters, which has the same section area with original DMT blade. But in C-squared time method, Dr. Schmatman proposed the use of Gupta's solution, which is based on the successive spherical cavity expansion theory. And by using this Gupta solution, we can consider the membrane positions. But Dr. Schmatman proposed the use of enlarged section area, 600 millimeters. So if we calculate an equivalent radius, it might be 24.5 millimeters. It is larger than the original section areas. So these figures reported by Bali and Scott. So this figure shows some distortion around the quant probe and dilatometers. So as you can see in the figure, so DMT developed maximum insertion borimetric and shear strains only about 1/3 from the CBT by Dr. Schmatman. So from this research result, we decided to use the original section areas, which means the same section area of the DMT blade. So and also we think about the membrane positions. So this is a research DMs can measure the pore water pressures in the center of the DMT blade. So we can find the penetration pore water pressures of DMT matches well with the pore water pressures of U3 position, not the U2 positions. So it means, so, and also, okay, next move. As you know, the pore water pressures around the cone dissipate the different speed with respect to the position. So excess pore water pressures in E3 position, so dissipate much slower than the C position, the U2 position. So it's more appropriate to consider the membrane position. I think so. Dr. Schmatman maybe proposed the use of the Gupta solution and consider membrane positions. So then I would like to point to one thing. So we can determine the coefficient of consolidation with respect to various dissipation, degree of dissipation. I mean the 20% and 30% and 50%, even in 60%, because we have some theoretical solution at that each degree of dissipation. But usually we determine the coefficient of consolidation in 1 point, 50% of degree of dissipation. But we calculate the excess pore water pressures with C50. So the dissipation curves does not match with the measured one, because we determine the coefficient of consolidation to match only 1 point. I'm sorry. So here we would like to propose some new method by using the optimization techniques. Basically, the idea is very simple. So we would like to determine the coefficient of consolidation, which minimize the differences between the measured and the calculated dissipation curves. So to do this, we have to update the coefficient of consolidation continuously until the differences between the measured and calculated pore water pressures minimized. In this research, I used the modified cavity expansion theory developed by Gupta to generate initial excess pore water pressure distributions. You can find these equations, and by using this equation, we can calculate the excess pore water pressure at an arbitrary point B in region cavity regions. And also, dissipation loss can be calculated with the governing equation axisymmetric, and it can consider the vertical dissipation of excess pore water pressures. They can solved by FDM after ADI method. And also, I compare the measured P2 values with the calculated excess pore water pressures at this point, 4 times of equivalent radius after tip, following the Dr. Schmatman's proposition. This is formulation of unconfined optimization problems. To solve the optimization problem, we have to define some objective function which should be minimized. It can be defined like this: square sums of measured and calculated excess pore water pressures. So we use early dissipation data then up to around 50% degree of dissipation. And to minimize these objective functions, we have to update the design values. In this research, we consider horizontal coefficient of consolidation as a design variables. Okay, sorry. And to update these design variables, we used VFGS optimization algorithm, which has been known as the most effective in solving unconfined optimization problems. This is a schematic flow of VFGS. With the particular coefficient of consolidation, we calculate the gradient vectors of objective function and calculate the norm of the gradient vectors. If the norm of gradient vectors is small enough, we are in convergence. So we determine that it is the optimized coefficient of consolidation. But the convergence is now obtained. We go to find some directions which minimize the with downslope of the objective functions. So with the first derivatives and second derivatives of objective functions. So after determining such directions, we find the alphas which minimize the objective functions in that directions. And with alphas and D, we can update the coefficient of consolidation and Hessian matrix we repeat this time. We repeat these ways until the norm should be converged. Here, now I'd like to show you some application result. This is the Yangsan site in Korea, east to southern part of Korea. Here is Korea, and there is China and Japan. The Yangsan site is a homogeneous, uniform NC clays, and you can find the geotechnical characteristics here. And there we carried out 6 DMTC and 6 DMTA method, but I'm just focusing on DMTC today. So we also took some undisturb samples to carry out the oidometer test. This is a typical Dilatometer penetration result. You can find that we have some crusted zones, but generally in this site can be classified uniform clay. This is dissipation curves. So as I mentioned, we carried out 6 DMTC method, so in 3 holes, so two times in 1 hole. So with these curves, at first we checked final P2 values converge to whether the final P2 values converge to the static pore water pressures or not, because this is the assumption of P2 log method. And we find the 50% degree of dissipation. So, and also the way the dissipation curves from the first and to 50 degree of dissipation, we used these measured values to find the coefficient of consolidation. This is the result. So we also calculated the coefficient of consolidation by P2 log method and C-square root method, and also as well as with a proposed method. So you can find that the x-axis means of P2 log method coefficient of consolidations. So you can find the Schmaltman coefficient of consolidation determined from C-square root method gives us a little larger coefficient of consolidation trend. And this is the trend of proposed method. It gives us 50% degree of dissipation, 50% larger than those P2 log method. But the coefficient of consolidation obtained from the autometers matches well, except one point. We check this point and find that there might be some disturbance during sample. So anyway, we can find the coefficient of consolidation determined from the proposed method can be determined very consistently. And I would like to say some advantages of proposed method. So with the optimized coefficient of consolidation, we can simulate generation of excess pore water pressures, and then also simulate the dissipation up to high degree of dissipation. And then we can compare the measured pore water pressures and calculate pore water pressures. Even though we used only the early part of dissipation curves, but we determined the coefficient of consolidation, which minimized the differences between the measured and calculated excess pore water pressures. So it matches until high degree of dissipation. So I mean okay. I'd like to conclude my presentation. So here we propose a new dissipation analysis method with the equivalent radius of 20.57 millimeters, which has the same section area. And we also use the Gupta theoretical solutions, which can consider membrane position and also simulate the penetration of braid. And by using optimization technique, which can consider the dissipation trend over some dissipation range, we can obtain the optimized coefficient of consolidation, which gives more precise, and the proposed method gives more precise horizontal coefficient of consolidations. And optimized coefficient of consolidation from the proposed method gives best matching dissipation curves with measured dissipation curves. And optimized coefficient of consolidation might be a representative coefficient of consolidation over entire dissipation range. Thank you for your attention.
I think this was a very interesting contribution, but I would have liked at the end perhaps to show in a diagram what you would have predicted by other methods, CH, and the range that you predict during all the consolidation, to have an idea of how much can be the difference if you interpret in the usual way or you interpret it in your way. Maybe you have shown, but I haven't not understood, perhaps. What I'm saying is some comparison between present methods and your method.
Yeah, I think this is a figure what you want. So this is a trend of the coefficient of consolidation determined from C-square root method compared to a P2 log method. So it gives almost 3 times larger than the coefficient of consolidation of P2 log method. And this is my trend. a little bit larger than those of pit road method, but with those matches with the kind of obtained from automated test. Yeah. Actually, this method, a similar method has been proposed several researchers. For example, maybe Dr. Battaglio from Italy, I think, so for the CPT, and also by the Professor Paul May recently, I think. But I also proposed this method to the CPTU, and I got a good result by using these kind of optimization techniques.
Why did you choose the C method instead of the A2 or the A method? Was there a conscious decision there, or just that was an accident?
You mean why I choose the DMT method?
Well, you tested in a clay, and in a clay, the expansion of the membrane back to the 1 millimeter point tends to add its own pore pressure back again during
Yes.
each phase of the test.
Yeah.
And it, I guess Dr. Schmertman and I have always thought that probably added additional time to the test or flattened the curve out. Maybe that the analysis of the curve stays the same, but I would think it would tend to flatten the curve, make the slope more gentle. If that makes sense.
So I'm sorry. So could you say again simply?
The expansion of the membrane each time in the C method,
Yeah.
you expand again to 1 millimeter,
Yeah. Yeah.
and that expansion itself should induce some additional pore pressure
Uh-huh.
during the test,
Yeah.
so that you impede or make slower the dissipation process. Now, it may be that we're analyzing really the shape of the curve, so maybe it doesn't make any difference in what we interpret for C sub H. But I was just wondering if you had a reason that you chose C instead of A2, for instance. You
So-
mentioned all three. I didn't know if you had a reason for that.
Okay, there might be some additional pore water pressures, but actually I didn't consider the kind of the gathering of the except pore water pressures. I just think about focusing on the PT values measured in the field.
Actually, the reason why we like the A method, A and deflate, we call it A and deflate method, so you don't have any further movement, are that to start with, there is already a theory available by Anderson for the circular probe. And then in the P2 method, you have to rely on what I think is a shaky assumption that the pore pressure, that the total pressure is equal to the pore pressure, which can be true for soft clays, but may not be true for stiffer clays.
Yeah.
So why to rely on the assumption that the total pressure is equal to the pore pressure when you can monitor the decay of the total pressure for which a solution has been found, though for a different shape? So we think is cleaner the A method, A and deflate. So you don't go to A to B, you don't expand. It's the same as measuring the decay, the contact total pressure, the decay of the contact total pressure as if it was a transducer, a passive transducer without moving anything. We think it's cleaner because has not an assumption of pore pressure equal the total pressure.
Yes, I know. So, so because that reasons you proposed the DMTA method, I know, and also I said DMTA method is applicable to Korean clay also, but I think we have to carry out more research to find some, the coefficient 7s to fit the Korean soils. So, and also I tried to this research because we can calculate and compare the coefficient, compare the excess pore water pressures with the theories, Is okay?
Any further comments? Thank you, Dr. Kim.
Okay, thank you very much.
I think Paula is going to present an interesting study. It's a field test in Venice.
Good morning, ladies and gentlemen. I'm talking about, I will show some comparisons of moduli obtained by DMT and from measurements under a full-scale instrumented test embankment located near Venice. And next, please. And this study is part of a research project aimed at characterizing the Venetian soils in connection with plans for the preservation of Venice and its lagoon against recurrent flooding. And it was carried out by 3 Italian universities with the contribution also by Georgia Tech. This figure shows the, yeah? Okay. This picture shows the location of the test site that was selected for constructing a test embankment, and this is the Venice Lagoon area. The site was selected because the soils at the site were very typical of the deposits in the Venice Lagoon area. Next one, please. So, a sand embankment of cylindrical shape of 40 meters diameter and having a final height of 6.7 meters and applied a total load to the soil of about 100 kilopascal, was constructed starting from September 2002 through March 2003. And the embankment was made by 13 sand layers of 4.5 meters thickness each one, and was covered on top by gravel layers. And the cylindrical shape was obtained by constructed geogrid reinforced vertical walls, and this in order to the cylindrical shape was selected in order to facilitate the interpretation of measurements according to common available, next one please, solutions for stress increments under circular load. So it was selected for this opportunity. Next one. This figure shows just a layout of the instrumentation. I won't talk in detail about this. The details can be found in the keynote lecture given by Simonini at the Porto conference. The embankment was extensively instrumented at the surface and down to 60 meters depth in order to measure total settlements, local vertical strains with depth by use of high accuracy multiple extensometers, horizontal displacements by inclinometers located at the edge of the embankment, and pore pressures by piezometers. Next one, please. The typical soil profile at this site is a characteristic of the soils of the Venice Lagoon area, which are highly stratified and mostly composed by sands, silts, and silty clays. But the silt sand is generally predominant in these deposits, and we will see that this characteristic has affected, influenced a lot the interpretation of the measurements. So this is a picture of the site at the beginning of the investigation before the construction, and this was the same view after the embankment construction. Next one, please. Several tests were carried out across the embankment area, including 10 DMT and piezo cone tests. Also, seismic piezo cone tests and seismic dilatometer tests were carried out along a cross-section of the embankment by Georgia Tech. And also some soundings were repeated after the end of construction from the top of the embankment. This figure shows the typical profiles obtained by DMT at the center of the embankment. It can be seen that the soils are highly stratified. and well-defined layer of homogeneous, let's say in some way, soil is detected in the upper 6 meters. Is this sand layer. This layer here between about 6-8 meters to 20 meters is mostly silt and was the layer where most of the settlements occurred during loading. And there is also a very soft clay layer at about 2 meters depth, and the soil, the deposit is normally consolidated or slightly over consolidated as indicated by the KD profiles. Next one, please. At this site, besides AB readings, also C readings were taken every 20 centimeters in order to obtain a more detailed soil profile. In fact, in this figure, we see the plot also of the C readings and the pore pressure index obtained from the C readings, the corrected C readings P2. And this profile is useful integration in situations like this to the profile of the material index because it shows a higher detail in soil profile. Next one, please. The soils are highly variable as shown by the DMT profiles, but in any case, the superimposition of all the 10 DMT profiles performed across the embankment shows that in some way this horizontal variability repeats, and there is some similarities also, but also some variability in the profiles. And it should be noted that these spikes observed in the value in the profiles of the CU and KD are due to the presence of thin stiff peat layers which are present in these deposits. Next one, please. In this case, several DMTA dissipation tests were carried out. We have been talking about this a few minutes ago. And the interpretation of these tests permitted to obtain the values of the horizontal coefficient of consolidation and permeability that were found relatively high, higher than usually in clays. Dissipations were run in the only in the cohesive layers, but in any case, the values obtained were rather high and anticipated that the consolidation could have been very fast. Next one, please. Another interesting information that we obtained from derived from the interpretation of the dissipation curves was in this figure. This is a typical DMTA curve at this site that is rather flat and is very different from the typical S shape that we usually get from DMTA curves in clays. And this behavior was interpreted as a signal of significant creep of a soil skeleton, and anticipated that the secondary settlements could be important, and this also was later confirmed by measurements. Next one, please. So these two people here, I see Paul Main is not here, but we're probably talking about shear wave, polarized shear wave propagation. So shear wave velocity measurements were taken by the Georgia Tech by seismic piezocone and seismic dilatometer test. Here there are some pictures showing the preparation of the tests. And next one, please. Carried out by Paul Main and Alec McGillivray from Georgia Tech, and this was the most exciting part of the testing program with the nice Venice seafood. Next one, and these are the profiles of the shear wave velocity obtained from seismic dilatometer and seismic piezocone along a cross section of the embankment. And next one. And this figure shows the values of the small strain shear modulus, which was derived from the measured values of shear wave velocity, also across a cross section of the embankment. Next one. Dilatometer tests were repeated after construction of the embankment in order to investigate the variations induced in the soil by the load applied by the embankment. And the truck was lifted up to the top of the embankment, and soundings were repeated from the top of the embankment nearby pre-construction soundings. And comparisons of the values before after construction is shown in this figure. The most interesting thing are probably the fact that there is a reduction in KD in the upper, in this upper over-consolidated crust, initially over-consolidated, that after loading tends to become normally consolidated. This indicates that the soil, the pressure in the soil under loading approaches the pre-consolidation pressure in some way. And the other thing that is the constrained modulus doesn't differ much after loading from the values that we found before the loading. And this behavior was interpreted in a way that the dilatometer modulus should increase with stress. But since the constrained modulus is obtained by a combination of the dilatometer modulus and the horizontal stress index, which decreases under loading, as shown by this profile, these two effects cancel each other, and the constrained modulus is substantially unchanged. Next one, please. We calculated settlements using MDMT, using the 1D approach before the field measurements were available along 3 sections of the embankments in order to account for the soil variability in some way. And these profiles show the settlement calculated by DMT along this 3 section. And the settlement at the center was calculated as 27 centimeters. This is only the primary settlements calculated by this formula. An additional undrained settlement of 2 centimeters was estimated by general consideration. Therefore, we estimated a primary and plus undrained settlements of about 29 centimeters. Next one, please, under the center. And this figure shows that the comparison of the prediction with the measurements. This is the settlement time curve measured at the center of the embankment during embankment construction and after construction. We have measurements available so far over more than 2 years from the beginning of construction, and monitoring is going to be to continue for I think 5 years after to go. And the DMT predicted the settlement of 29 centimeters at the end of construction, while the measured settlement was 36 centimeters after the end of construction, which occurred in 6 months. This figure shows an important characteristic of these soils, that secondary settlements are very important. The total settlement measured at the last available reading that we have was 48 centimeters. 12 centimeters developed after the end of construction. And since we have piezometer measurements throughout embankment construction and subsequently that indicated no detectable excess pore pressure in any layer due to consolidation during construction and after construction, we presume that the construction occurred essentially in drained condition, that consolidation was fast as anticipated by the DMT value, DMTA dissipations. And so these settlements is due to secondary settlements, and which is so about 25% of the total settlement measured so far is secondary settlement. And we presume that a significant secondary settlement should have occurred also during construction, contemporary with primary So it's very difficult to separate the two contributions to interpret this first part during construction in a straightforward way. Anyway, the comparison between settlement predicted by DMT, which does not include secondary during construction, and these measured values is substantially in acceptable and good agreement. Next one, please. These figures show the local vertical strains measured under the center of the embankment at 1 meter depth intervals by high accuracy multiple extensometers and the corresponding accumulated settlements. We can see from this figure each curve refers to each load increment of construction of the embankment. The bold line refers to the end of construction, and the dotted line on the right refers to measurements after under constant load. So we can observe that the vertical deformation are mostly concentrated in this layer of silt layer between 8 and 20 meters, and also in these very soft clay layers at about 2 meters depth. And deformation measured at the end of construction was in these layers was about 3 to 5%. Next one, please. Measurements indicated also that deformations occurred mostly in vertical direction, because the horizontal displacement measured by inclinometers at the edge of the embankment showed horizontal displacement one order of magnitude lower than the vertical displacement. And this can also be seen, next one please, by this settlement profile measured across at the end of construction across this cross section of the embankment. So it can be seen that the pattern of deformation is substantially vertical. Next one please. So this is a comparison of the constrained modulus MDMT obtained by the sounding at the center of the embankment with the modulo, one-dimensional modulus back calculated from the measured vertical strain according to this one-dimensional expression. We assume that this was substantially correct in view of the fact that the deformation were mostly vertical, as I said before. Well, this comparison shows that there is, of course, some discrepancy, but it should also be noted that the MDMT values were obtained every 20 centimeters, while the measured the moduli back calculated from measurement were obtained over a depth interval of 1 meter. So are some average measurements. Well, in any case, the overall comparison is not so bad. Maybe if we go to the next slide, we can see this is the same comparison. Is a comparison of vertical strains and settlements calculated by DMT and measured at the center of the embankment. We can see the comparison in terms of vertical strains calculated and measurements is substantially shows a good agreement. We see there are some underestimates here and overestimates here that finally partially compensate when we obtain the total settlement by summing the vertical strains. Next one, please. Next figures. In the next figures, the comparisons are shown in terms of Young's modulus instead than of 1D modulus. This figure shows the variation, the figure on the left, the variation of the second Young's modulus back calculated from local vertical strain measured at the center of the embankment under various loads throughout the embankment construction. So the red curve is the initial modulus obtained from the Young's modulus obtained from G0 from shear wave velocity measurements, as plotted here as a reference. The black curves represent the modulus back calculated from measurements at under each load increment of the embankment, and the bold line represents the end of construction, and the blue profile represents the the Young's modulus corresponding to MDMT and under the center of the embankment. So the figure shows there is a progressive reduction in modulus under increasing loading. The variation of modulus should reflect two effects: a variation of the increase in stress level due to the embankment load, and the increase in strain level due to deformation. So in order to try to separate the two effects, we try to isolate the contribution of the stress level by expressing the Young's modulus in terms of Yambus, the simple Yambus expression in terms of modulus number, in order to isolate the effect of stress level. So this figure shows the variation of the modulus number corresponding to the Young's modulus under various load from the beginning. And this figure also shows that there is a reduction of the modulus number under increasing loading. The next step was to try to derive curves expressing the variation of the soil stiffness with the strain level from the measurements. And this figure refers to a soil layers, the upper soil layers up and down to 8 meters. Each curve represented here is obtained from measurements and represent a measured curve at a given depth. And the variation, the decay of the soil modulus are expressed in terms of variation of the modulus number at each depth as a function of the vertical strain measured at that depth. So it can be seen that each curve shows a reduction with strain. The circles in the same colors on each curve correspond to the moduli obtained by DMT at the same depth, expressed. They also have been normalized to the vertical stress, expressed in terms of soil modulus number. These values were superimposed to the curve, until they intersected the curve from measurements at the same depth, in order to try to locate the abscissa of these values, in order to identify a possible range of variation of the vertical strain corresponding to this moduli. And in this case, we can see that the variation of the strain range is from about 0.01 to 0.5% in this case. And the next figure shows, next one please. Next one please. No, there was one before. Yeah, this one, thank you. And represents the same curves for the layers from 8 to 20 meters, the one giving the most of the settlements. And it can be seen in this case that the data points corresponding to DMT moduli are located in a very relatively strict range, and the strain range in this case is 0.5 to 1%. And can be seen also from this curve that the initial part of the curves is missing because the instruments were not able to measure very small strain below this level. But anyway, the curves show clearly that there is a decay in soil stiffness. Next one, please. And this one is refers to deeper layers. Of course, the deeper layers are not so interesting like the upper layers. So as conclusions from what we have found so far, we found a good agreement between settlement measured at the end of construction and predicted by DMT net of secondary during construction. And also, we can say that we have found an overall satisfactory agreement between profiles of MDMT and moduli back calculated from vertical strain measured at every 1 meter depth at the end of construction. Field measurements have shown a progressive reduction of moduli back calculated from measurements under increasing load. And in-situ curves of decay of soil stiffness with strain level were tentatively reconstructed from the measured deformations, vertical strains measured at every 1 meter at the center of the embankment under each load, embankment load throughout the embankment construction. And from comparison with the observed in-situ decay curves, we have found that the DMT moduli could be possibly located in a strain range from 0.1 to 1% and 0.5% on average. And this could be a first step, first indication useful in view of the tentative of deriving in-situ decay curves of soil stiffness with strain level from seismic dilatometers. Of course, these are just preliminary evaluations, so if anybody has comments or suggestions for a better interpretation of results, is welcome. Thank you for your attention.
And I was just wondering if you had any pressure cells at the base of the embankment, because we didn't see any data from those cells.
Yeah, I haven't shown details on the instrumentations because I wanted to focus mostly on the interpretation of the DMT data. But there are a lot of data about instrumentation that maybe you can find in the also in the papers by the people of Padova University, Simonini in a keynote lecture in Porto. They have followed all the monitoring process, so there are a lot of details on the instrumentation. I haven't included it in my presentation because there was no time to say everything.
Yeah, I appreciate that, and you and I can get together afterward. But just a quick thought here, because we're looking at settlement, which is a function of the vertical stress. So that curve you showed, the construction progress going up to the 6.7 meters. If we could have like a companion plot that shows the increase in, you're going, yes, okay.
Can you go back to, okay.
Right, that one there. If we could have like a companion somewhere to show the increase in the pressure at the base, so someone in the audience could see the increase in stress, and then we'll get a better feel for the settlement.
Yeah, there are some disinformation. We have this information, but I haven't shown it yet. But it's exactly as you say.
All right, thank you so much.
Thank you.
Does the creep bear any relation with the granulometry of the different layers? And secondly, it seemed at one point that the sand layer on top yielded under just 100 kPa. Is that what's your take on that?
Can you repeat the second one?
I'm a little bit surprised that a layer that seemed to be just sand yielded under 100 kPa.
Okay, just the first question was about secondary. The secondary settlements here have been studied a lot by Paolo Simonini, Simonetta, Cola, and they have shown in a paper that substantially secondary coefficients are similar in the various layers. So the effects of soil type. Soil types are different, but anyway, they say that the original, mineralogical original of these deposits is the same, despite of the grain size. And they also have found, have compared the secondary coefficient from laboratory and from the interpretation of these measurements at each depth. And they have found substantially comparable values in the various layers. So
there's no relation between granulometry and secondary?
Not as far as I know. Yeah, as far as I know, they found this not much influence of grain size because the origin of the was the same. And
For the sand, yeah. I mean, for the sand, 100 kPa yielding, is that normal?
what?
I mean,
Can you tell me? Can we
yeah, the
take
reduction of KD? I mean, that was.
yes, for the reduction of KD.
First of all, you can hear me?
Yeah.
The embankment will be unloaded probably in fall of this year. And what is important for Paula and Silvano, the embankment will be unloaded in steps, in 3 steps, each step 2.5 meters approximately. And after the second step of unloading, it will be a reloading of the same amount. And the whole operation will take about 8 months. And during this operation, the owner, the Consorzio Venezia Nuova, the general contractor building the gate protecting Venice against flooding, will perform, if I am well informed, the seismic cone penetration test. I believe that it will be very worthwhile for you to be on the site and to perform the seismic dilatometer, at least after the second stage of unloading, after the reloading, and after complete unloading. It will be very important. The second question is the settlement, the secondary settlement are continuing with a quite important rate, and as Paula has mentioned, the secondary compression measured in the field is 50% higher for cohesive layers as compared to the secondary compression measured in laboratory. On contrary, even the precision of the measurement in more sandy layers is not extremely high because the values are very small. It seems that the secondary compression measured on more silty sands in laboratory, and the silty sand samples have been extracted from the ground and drained a little and thereafter frozen in order to obtain something which is probably not fully undisturbed samples, but better than normally retrieved sample. For these sandy samples, the C alpha in laboratory and C alpha in the field seems to be comparable. First of all, you can see that this is a plot of the settlement in the center of embankment up to 2005, and the secondary settlement is proceeding at quite high rate. Can you show the next? The next. The next. First of all, these are the odometer curve obtained in situ for this clayey soil between 8 meters and 12 meters, and the corresponding pre-consolidation pressure. And I believe that for the clay you have the opportunity to make a very precise and reliable comparison here for different stress level during the loading and at constant loading. The next. The secondary compression curve measured in situ, the next in this clayey layer. Okay, here you see two information. On your right, this C alpha epsilon, not C alpha E, measured in situ over the value measured in laboratory. And you see that for clayey soil, for fine-grained soil, to be enough generic, you have much larger secondary compression in the field, while for sandy soil, the values are very close to the measured in laboratory. Here you have also the recompression ratio, RR, measured in laboratory, divided by the recompression ratio measured in situ. And for both sandy and fine-grained soil, this ratio is very high, confirming the old perception, or starting with Zaghi and Peck, that in the recompression range, below the yield or pre-consolidation pressure, we generally overestimate to a large extent the settlement. This is the situation, and C alpha for sandy soil is more or less the one measured on these semi-indisturbed samples frozen after extraction from the ground. Thank you.
Well, whenever you reload a crust, you rejuvenated it. Because if you think of the definition of over-consolidation ratio, is the maximum past pressure of the present pressure. So if the maximum past pressure is exceeded, the soil is rejuvenated. This is the reason why KD decreases. What Paula said was there was a compensation because the stress increase produced an increase in modulus in general. But since you are approaching the pre-consolidation pressure, there was a reduction. So the two effects compensated. So the interpretation was appropriately leading to an M modulus which did not vary, because on one side was the increase in stress, but on the other side KD appropriately reduced the factor Rm. So this is the reason, but this was already said by Paula, why M did not increase a lot, while KD surprised us initially. Why KD decreases? Well, the crust are cancelled when you put a load on them.